All right. Good afternoon, everyone. Welcome to our USEA Consensus webinar, the Developing Hydrogen Economy, Potential, Progress, and Changes, co-hosted with ORIC and Guidehouse and moderated by Mr. Peter Connors, tax partner with ORIC, and our Mr. Mike Moore, program director with USEA. So for those of you who don't know me, I'm Michelle Littlefield. I'm a program coordinator with the USEA Consensus program. Just a note about what we do, we're formally named the Building Consensus on Carbon Capture, Utilization and Storage, CCUS, and Clean Coal Technologies. We call this Consensus for short. This is a cooperative agreement with the Department of Energy, Fossil Energy. The program seeks to educate the public, policymakers, industry, and stakeholders on CCUS and clean coal technologies by hosting webinars such as these, along with a series of monthly educational briefings, conference workshops, technical reports, and we have a monthly news clips that we release of CCUS and clean coal related updates. If you have not done so already and would like to join our mailing list, feel free to send an email to the address at the bottom of your screen and we'll add you as a subscriber. At the end of the session, we'll have a question and answer portion. Please use the Q&A box at the bottom of your screen to submit a question and we will address as many as we can. This webinar will also be recorded and posted on our website, as will the presentations, but we appreciate you taking the time to join us live. With that, Mike, it's all you.
All right, Michelle, thank you very much for the kicking us off and getting us down the road. We've got quite a group assembled today, and the topic's hydrogen. In fact, I think it's such a popular topic. There's probably about 4 of the hydrogen webinars going on today about the same time from what I can figure out. But the difference is we've got the key players here today. Peter from ORIC is going to take the group through this, and Robert Selinsky with Guidehouse has been a big piece of assembling this group, what we have in front of us today. I have a keen interest. CCUS at some point down the food chain of things may be involved as a way of some routes of hydrogen getting into the hydrogen market. So keen to see what happens here. Been running with them as they've been putting their decks together, and I can assure you it is deep, rich, and full content that don't blink. There's a lot here. And with that, I'm going to turn it over to you, Peter.
Thanks, Mike. So let's just go to we'll go to the next slide. We've got our speakers and I'll go through the agenda, just running through it quickly. First, we're going to start out with a presentation by Rob Selinsky from Guidehouse, which is a prominent energy consulting firm. And Rob is going to give a primer on the hydrogen market and the colors of hydrogen. Then the next topic will be regarding hydrogen's economic potential, and Ruth from NREL will discuss a report called H2 at Scale, published by the National Renewable Energy Laboratory, that's NREL, which looks at the potential for integrating hydrogen throughout the economy, including both the electricity and energy sectors. And according to the report, by the year 2050, hydrogen is expected to account for 17% of all energy sources, even without a national cap and trade program or carbon pricing. So Mark will lead us through the report. We'll then go to Sonal Patel from Power Magazine. She'll give us an overview of industry expectation on the cost of hydrogen based on recent developments. Then Ryan McCarty from Honda and Bob Weiner from Toyota will showcase their entries into the quickly developing hydrogen-based transportation sector, and we'll discuss how the automotive industry will help decarbonize the transportation industry. And then finally, I will give a quick overview of the prospects for tax incentives for hydrogen production and usage. And then, of course, at the end, there'll be 10 minutes for Q&A. So with that, let us now turn to Rob Selinsky's presentation. Rob Selinsky is a managing consultant in the Boulder office, Guidehouse. Rob has worked in the energy sector for 15 years, and he was really instrumental in putting together this program. And so, Rob, I'm going to turn it over to you.
Thank you, Peter. Good morning, good afternoon, everyone. Rob Selinsky here. As Peter said, I'm a managing consultant at Guidehouse. And lately, I've been working on hydrogen projects on the utility side of things. as well as trying to help orchestrate some commercially viable sort of multi-stakeholder hydrogen ventures. So as mentioned, my portion here today is to give a general overview of where hydrogen is right now, some of the important components and important drivers for the future. I also want to preemptively apologize for going through some of these kind of quickly, but we've got a lot of really great experts on the line today who will be diving into specific topics a little bit later on. So let's get started. Next slide, please. So from our view at Guidehouse, the drivers for adopting hydrogen are really inherent to the energy transition as a whole. And the easiest way for me to think about hydrogen is as a source of dispatchable clean energy. Electrification, it's a pretty straightforward and often elegant solution in a lot of cases. But as we see it, there's always going to be a need for more portable and more on-demand solution for clean energy. When I need a personal and tangible example, my mind always goes to taking a road trip. So I've got an electric car. I really love it, particularly for driving around the city. But if I'm going to be taking a road trip, I'm in Colorado, that might involve venturing more off-grid. I'm more likely going to want a gas-powered vehicle, at least at this juncture. So hydrogen as a portable gas that can really carry a lot of energy and can also be sourced from 100% clean energy is a great candidate for these kinds of applications. So the 5 key elements that I'll be discussing today are supply. Where are we sourcing hydrogen from? Where will we source it from in the future? Demand, who's going to be using it? What are the best use cases for hydrogen? What kind of infrastructure is required? What kind of policy and investment is required, and what's already happening in that space? And then how does this fit into our broader economy-wide decarbonization plan? Next slide, please. So hydrogen can be produced, and it already is being produced in a bunch of different ways. The easiest way to think of these is by color. So gray hydrogen is produced from regular fossil fuels. Usually that's natural gas. It's how it has been done. It doesn't really bias anything in the way of decarbonization. Blue hydrogen is similar, but on top of that process, we have a carbon capture and storage element. So that's helping to lower overall emissions. Similarly, turquoise hydrogen, also from natural gas, from a different low carbon process. Green hydrogen is sourced completely from renewable energy, and pink hydrogen is from nuclear. So these bottom 4 here on the right are what we consider low carbon hydrogen. Next slide, please. So I mentioned that we're already producing kind of a lot of hydrogen. As you can see on the left side of this graph, most of it is produced from natural gas. Almost all of it comes from fossil fuels. On the right side, you can see what that's being used for currently. So most of the pure hydrogen we produce goes towards petroleum refining, goes towards ammonia to make fertilizer. There's another sizable chunk of blended hydrogen to make certain chemicals and some other more niche end uses. Next slide, please. So the previous slide was the whole world. This is the picture in the US. Again, most of our hydrogen comes from fossil fuels. Most is used for refining and fertilizer. You'll see on the map that a lot of that's focused around the Gulf of Mexico, but there are some hubs elsewhere in big population centers. However, there's also a big opportunity to produce and utilize low carbon hydrogen, as we can see on the right. Experts are forecasting that we may start out working with biomethane to make hydrogen and then move on to mostly electrolyzers and thermochemical processes as the industry matures. Next slide, please. So this is a real simple one. This is where we think we're headed in the future. So in terms of future growth, the experts, and for this graphic, that means Bloomberg, see that almost all of the growth is going to come in the form of transportation, including a lot of heavy transport, also power generation, and just a little bit in buildings. I mentioned previously that there are certain applications that are easier to decarbonize through electrification. Buildings is definitely one of those. But the projection for hydrogen is that growth will come in some of these other harder to electrify sectors. I also wanted to note that these orange bars on the left, they're about the same size now as in the future, but we're anticipating that most of this hydrogen, industrial hydrogen use will be shifted away from gray hydrogen and into that clean green hydrogen. Next slide, please. So this is kind of a roadmap that shows how hydrogen production could ramp up and evolve as it gets to be more mature. So we start over here on the left, and then as we move into the future, we're moving further to the right. Now, the first and the simplest use of low carbon hydrogen would be industries that already use hydrogen. These are things like refining, ammonia for fertilizer, chemical manufacturing. And the benefit here is that these people are used to working with hydrogen. They've already got their on-site infrastructure and all their processes already dialed in. The second most likely use case is for transport. Again, mostly talking about heavy transport, long-haul trucking, heavy-duty construction type machinery, but also definitely things like fleet vehicles, public transportation, personal vehicles too. We've got some great experts to talk more about that a little bit later. The third application is for power generation, both in terms of a low carbon energy source, but also a big component of grid resilience, as we see being a really big recent factor in Texas and other places. And then further into the future, we think we'll be seeing hydrogen used more for big, high temperature industrial processes, even used for energy distribution, acting similarly to how the natural gas grid works today. Next slide, please. And in terms of infrastructure, there are a lot of words here on the slide, but I mostly want to emphasize that proper infrastructure is absolutely crucial to widespread adoption of hydrogen. We'll need something that connects the supply and the demand while also thinking about things like storage, proper tagging and tracking of hydrogen too. Next slide, please. Fortunately, some of our colleagues over in Europe have created a blueprint for how to think about these infrastructure type requirements. I'd highly encourage you to look up and read the European Hydrogen Backbone Study, which envisions a large-scale network in Europe that both repurposes existing pipelines and corridors, but also analyzes the need for new infrastructure in order to decarbonize the entire gas system. Next slide, please. And then when we think about large-scale infrastructure here in the States, we're also obviously going to need to consider large-scale storage. So unless we can perfectly sync up the supply and the demand, we're going to need storage. A lot of companies have been looking into this, particularly underground storage in used natural gas reservoirs that are depleted, some underground salt formations, et cetera. And there's actually some pretty reasonable and favorable geography on our side, also in Canada too. Next slide, please. And then I mentioned storage. We're not only talking about storing hydrogen, but also storing captured carbon. Of course, if we're talking green hydrogen, sourced completely from renewables, there's no captured carbon involved. But we do think that during the transition to wider hydrogen adoption, and even more likely in traditional fossil fuel states, blue hydrogen may be the more likely first mover. Technologies are moving pretty quickly on this front, and there are both above ground and underground methods for storing captured carbon under development. Next slide, please. And then this is one that I did not mention on the commercialization roadmap slide. But another near-term end use is to blend hydrogen into the existing natural gas supply. And even at a pretty low percentage, you can actually burn quite a lot of hydrogen and therefore start to decarbonize the entire natural gas system pretty significantly. There are a bunch of pilots underway. Most of those are in the UK. but also in Canada, some in the US as well. And the preliminary results are actually pretty promising. We may be able to blend up to about 20% hydrogen into natural gas without having to convert major conversions of end-use appliances and infrastructure. However, since this is a relatively new concept, hydrogen is a much smaller molecule that behaves differently than natural gas. We definitely want to pay attention to the research here and do a full due diligence before rolling these kinds of things out. Next slide, please. So on the policy side, things are definitely ramping up. We're seeing a lot of new federal action, which I will let Peter discuss a little bit later. There are also a ton of investment and ESG related trends. In fact, just yesterday, I saw an article in The Guardian that was titled, "Shell Faces Shareholder Rebellion Over Fossil Fuel Production." There's also increasing customer awareness and customer preferences, pretty rapidly accelerating technologies available, but also we're seeing accelerating climate consequences too. So we think that all of these are pointing in the same direction and giving hydrogen some pretty strong tailwinds. Next slide, please. So in the US, at least, a lot of current action is being driven by individual states. I'm not going to read all of these right now, but they're not even necessarily the states that you would most suspect. And that's kind of what I wanted to highlight here. Let's go on to the next one. There's also a lot of collaboration between public and private sectors. We're seeing a lot of multi-stakeholder projects, innovative pilot projects. I know that Mark is going to dive deeper on H2 at scale in just a minute, but there are a lot of good projects underway in space that involve a lot of good collaboration. Next slide, please. And then another group is utilities. Utilities are also driving a lot of action on hydrogen. I want to say that I could have chosen many different projects here to showcase. That list is growing daily, but these are some of the most notable ones. They involve large-scale electrolyzers, conversion of existing power plants, hydrogen blending, even biofuels. And next slide, please. So to kind of conclude this introductory section, we have a lot to do if we're going to decarbonize the entire economy. Efficiency is a huge component. Electrification is a great fit for a lot of different end uses. Hydrogen is definitely not the only tool that we have at our disposal, but it can play a big role in a lot of these steps, particularly things that are hard to electrify, things that require long-term or seasonal storage, very high temperatures, or involve long distances or remote locations. It's definitely a big challenge, but we've got some good options. Next slide, please. So with that, I'm going to pass it over to Mark Ruth to talk about technical details and some economic potential.
Yes, thanks, Rob. And I'm just going to introduce Mark in the next few minutes. And you actually saw Mark's topic on the prior slide, H2 at scale. Mark is a group manager in the Industrial Systems and Fuel Cells Group at NREL's Strategic Analysis Center. He leads analysis projects focused on the interface between energy sectors, including electricity and energy. And I think there are many people that have heard of NREL, but it'd be good to begin, Mark, with just a little introduction into what is NREL and what types of projects and resources are available to the general public through NREL. And I have to tell you, I'm a devout fan of the H2 IQ programs. Listen to them every Sunday, driving my wife crazy. So, Mark, I'll just hand the podium over to you.
Thanks, Peter, and thanks, Robert, for such a great introduction to the topic as a whole. As Peter mentioned, NREL may be something you've heard of, but may not be familiar with. We are one of the Department of Energy's, the U.S. Department of Energy's 17 national laboratories. Back when I first started NREL 20 plus years ago, I used to say we were the smallest, the youngest, the only one without a nuclear program, because back then most of the laboratories were really the kind of the traditional Manhattan Project laboratories, Oak Ridge, Pacific Northwest, which is near Hanford, Los Alamos, Sandia, and those types of labs. NREL was created as the Solar Energy Research Institute in the mid-70s, as it sounds, to focus on renewable energy and energy efficiency technologies. We're located, our primary site is located in Golden, Colorado. We've got another site very close to Boulder, Colorado. We've got people now in California and DC and other places of the country as well. We've got a total of about 2,400 employees. It goes up and down depending upon how many postdocs we have and other people working. The primary focus of the lab is really developing technologies in these renewable energy and energy efficiency areas. So a lot of the solar energy development is out of NREL. There's wind technologies that are being developed and tested over the years at NREL. Building efficiency, vehicle transport, both autonomous and battery electric vehicles. And then of course, fuel cells, electrolyzers, and others like that. My group specifically works on analysis and thinking through some of the problems with the energy system as a whole. And this work that I'm going to present in the next few minutes is really an overview and a summary of a report that we published last October. And you can see the URL near the bottom of this slide, the one that ends 77610, that summarizes the report and everything else. It's Peter tried to print it out. It's 160 or so pages, so I don't recommend printing it, but read the executive summary and look for any other details you might want to be able to dig in more deeply into the analysis and the effort as a whole. Next slide, please. So the overall analysis was really to try to understand the technical and economic potential of what we with the Department of Energy are calling the H2 at Scale initiative. Robert mentioned some of the projects that were funded, or at least one of the funding calls, with 18 projects and $20-some million under H2 at Scale. But H2 at Scale is bigger than just those. It's kind of an overall DOE initiative that I like to think about and like to discuss as using hydrogen as an energy intermediate. We're all familiar with electricity as an energy intermediate. We don't get electricity as electricity, which would be really difficult to do unless you're Ben Franklin getting it from lightning. Instead, we make electricity from other sources, fossil sources, renewable using solar PV and wind, hydro, and nuclear sources as a whole to be able to make electricity. And then we utilize electricity for all the applications that we all know that we use it for. Hydrogen could be a complementary intermediate in that it can be produced from all those sources, can be produced directly from electricity, but that it also goes to a number of different products. The reason why it complements electricity is because it can be inherently stored, and it has a chemical opportunity. So in other words, the hydrogen molecule can be used for a lot of options. Here on this slide, you can see on the left side, really, we talk about the number of different sources going through electricity, either directly or indirectly, directly to hydrogen. And we talk about that like steam methane reforming of natural gas. We talk about nuclear generation and direct high temperature options to produce hydrogen. Or we go through electricity and then via electrolysis to hydrogen. And then hydrogen is used for a number of purposes. As Rob mentioned in his deck, right now we use about 10 million metric tons per year of hydrogen, on-purpose hydrogen today, primarily for petroleum refining. So you see that kind of upgrading oil in the upper right of my side, and making ammonia for fertilizers, as you can see in the top purple one. There's a lot of other options for utilizing hydrogen. Transportation in light duty, medium, and heavy duty vehicles, combined with carbon dioxide to produce synthetic fuels, upgrading biomass to be able to get more fuel per acre of land from biofuels. Ammonia can be used not just as a fertilizer, but also as an energy carrier for a fuel. One of the interesting areas I really like is around metals production. Steel today is one of the most polluting industries, or one of the most polluting sources in the world, both in terms of greenhouse gas emissions, where it's somewhere between 5 and 8% of total global greenhouse gas emissions are from steel production. And if you look at pictures of, say, Beijing today or Pittsburgh 100 years ago, the primary air pollutant that caused all that smog was not transportation or electricity production. It is actually steel production because of all the coke and coal that is used. You could use hydrogen instead. And then there's obviously a lot of chemical processing and then heat and distributed power. One part of this analysis was the technical potential of hydrogen. And Rob showed around, he put his numbers in megawatt hours, going from 10 million metric tons per year, which is like 3.5 megawatt hours per year in the US, to what I calculate to be around 70 million metric tons per year. Our kind of top end analysis, not thinking about economics, is really focused around, our estimate around was really around 110 million metric tons per year. So you can see that growth of 10 plus times, 7 to 10 times is really possible, depending upon the policy drivers, the growth of the industry, the economics of synergies, the ability to develop the infrastructure, things like that, but it can be much larger. Most of our work that I'll talk about, though, in the rest of this presentation is really the economic potential, where we start to think about the economics. Next slide, please. So one of the challenges with economics for hydrogen historically, and most of this work was done without really considering greenhouse gas issues and other things, was really around the fact, and you can see that in the right bar over here, is that C-methane reforming is a well-known technology. You take natural gas, you reform it, you make hydrogen. We do that very efficiently. We do that at 10 million metric tons per year, which is actually around 2% of our total energy use today within the US. And we use it for refining and ammonia in that space. Other options have the same problem, as you can see in the left-hand bar here, which is the way we used to think about electrolysis, or low temperature or LTE electrolysis. There we were taking electrolyzers, running them the full time out of the year, relatively high efficiency at 66%. Capital costs you can't achieve today, but today's technologies are around at $400 per kilowatt for the system, and a cost of electricity that you would pay for full-time electricity at 6.5 cents per kilowatt hour, which is industrial rates, the average industrial rate in the US today. As you can see from that, the all-in cost of hydrogen is $4.20 per kilogram, and is no way competitive with the less than $2 per kilogram C-methane reforming can get. However, as we've thought about that, the world is changing. Electricity prices are going down and getting more volatile, especially as wind and solar technologies are being added to the grid. And with the electricity prices going down and getting more volatile, we're starting to see other opportunities. If you were able to get on this wholesale market in many parts of the country, you could get 2 cents or 1 cent per kilowatt hour electricity for somewhere between 20% of the year and say 40% of the year in places like the Texas Panhandle. We actually get higher than that on average. You can get about 50% of that. If you took the lowest cost electricity for half the year, your average price would be less than 2 cents per kilowatt hour. And if you did that and you operated your electrolyzer as a dispatchable load, you get this second pair of bars here with 277 and 224. What happens is we assumed the same type of lifetime for the electrolyzer, a 20-year lifetime, but because you're paying less for electricity and you're only running it part of the time of the year, you actually bring your overall cost down. You bring down your electricity cost fraction down quite a bit, but you've got to pay more capital because you're producing only 40% of the total number of hydrogen molecules over the course of the lifetime. Now, we believe that as national lab researchers, if we can do anything, we should be able to bring down capital costs, even if we have to take a hit on efficiency. And so that moves from the second to third set of bars here. And there, the capital cost of the electrolyzer is reduced by 75%. We've done about a 90% reduction in terms of similar fuel cell technologies for vehicles over the last 15 years. So 75% seems possible. And that brings the price down to, as you can see, very, very competitive with C-methane reformed hydrogen. And that's without CCS. If you add CCS, it's probably even more competitive as you think about this problem. So this really shows some of the economic potential and some of the opportunities for making hydrogen and where that fits. Our analysis in terms of the economic potential, which was the URL I showed on the first slide, and if we can go to the next slide, please, really focus on what is the economic potential and what might some scenarios look like for the economic potential? Next slide, please. Obviously, there's a lot of caveats around any analysis, a lot of limitations of any analysis. The key ones I want to point out here is that we looked at a market equilibrium methodology. We did not look at build out rates and transition reductions in terms of stock turnover, those types of issues. Nor did we look at policy drivers such as emission policies. So this was just looking at hydrogen and how it might compete in the world that existed 9 months, a year ago, with almost no emission policies and with very low cost natural gas. Obviously, there's a ton of assumptions. We limited our analysis to sectors that could be forecast, and we had to deal with delivery costs because the infrastructure is one of the key challenges within it. But in doing so, if we could go to the next slide, please. In doing so, we developed 5 different scenarios that tried to look at what the future might be and how that might play out. Those scenarios you can see are listed on the left. The reference scenario, which was kind of a business as usual today, how the future might play out in 2050, looking at no changes from today, low cost natural gas, no carbon policy, nothing like that. And R&D advances an infrastructure scenario that started to look at, well, what happens if R&D improves and infrastructure for light duty transportation and medium heavy duty transportation using hydrogen fuel cells were built. A high natural gas price scenario, which the Energy Information Agency out of DOE likes to call their low natural gas resource scenario, and that has higher natural gas prices. An aggressive electrolysis R&D scenario, which is reducing the electrolysis price by 50%, and a lowest cost electrolysis scenario, which is like a 75% reduction in electrolysis prices based on R&D. And you can see the results for those 5 scenarios on the right. In the bars, the left-hand set of bars is the demand, which are the ones with the multicolors, and the supply is the ones with the brown, mustard, yellow, and green bars. And you can see the size of each one of those. The x-axis of each one of those is the size, and for each scenario, the supply equals the demand, so those sizes are equal. As you can see in the reference scenario, the growth that goes from 10 million metric tons per year to about 22 million metric tons per year, primarily based on growth in the biofuel sector. So if there's biofuels for aviation, which we see going forward, there's hydrogen demand for those, you utilize the hydrogen. But also some of the chemical sector like methanol, which you can see in the little orange bar on that top demand bar itself. However, all that supply comes from steam reforming of natural gas. If there's advances in infrastructure, then there's additional growth within the markets. There's metals, which goes in, which is reshoring steel production using hydrogen instead of coke, and there is some in the light kind of turquoise color for light duty fuel cell vehicles, and in the purple color for medium and heavy duty vehicles. The supply is still mostly natural gas steam methane reforming. However, the market is getting large enough, we're starting to drive the price of natural gas up, and hence we start to see high temperature electrolysis using nuclear generation as a key opportunity and driver there. In the third scenario, we looked at higher natural gas prices, which meant that the cost of the supply went up, the demands went down because it was harder to compete with some of the competing technologies, but we see a bigger separation and much less natural gas production, much more high temperature electrolysis use using nuclear energy. The fourth scenario, we start to see low temperature electrolysis utilizing some low cost dispatch constrained electricity, or electricity that either wouldn't be built out or would be curtailed from renewables in the green bar, and it competes in both. It brings down the overall price of hydrogen, but not enough for the markets for the transportation to continue to grow. And then the lowest cost electrolysis scenario, you really see with low cost electrolyzers, a lot of low cost dispatchable energy. It's out competing natural gas prices, even without other policies, and it out competes some of the high temperature electrolyzers. But one of our findings is that incentives are needed for hydrogen to compete for things like long duration storage and dispatchable electricity generation, because without those, without incentives, we really don't have a driver to go to, say, 100% renewables. Also, the same problem with generating heat or supplementing natural gas. Again, without a carbon driver, it's really hard to go to replacing natural gas with these types of other types of technologies that are a bit more expensive when you don't internalize those externalities. Next slide, please.
And just before we leave that, I'll just comment that your figures are a little more optimistic than the Bloomberg figures that Rob discussed earlier. And of course, that really just depends on the assumptions, doesn't it? Really.
Actually, Peter, they're a lot less optimistic than the Bloomberg numbers and Rob's numbers. And the reason for that is that I report it in millions of metric tons per year, which is kind of a standard hydrogen market number. And they report it back in megawatt hours per year. So his 30, I think it was 35 megawatt hours per year, or 23,200 million megawatt hours per year. That's really around 75 million metric tons per year, which our highest number was more around 40 million metric tons per year. However, as I mentioned before, we did kind of a non-economic scenario that got up to 110 million metric tons per year. So it really shows you a lot of information around economics, around other things.
Thanks for clarifying.
This slide here is really intended to show that not only does adding electrolysis, and the right-hand bar is the one to focus on here, not only does adding electrolysis increase the amount of wind energy for hydrogen production, but it also increases the amount of wind energy for electricity, because you build some wind energy that wouldn't be built if electricity is the only market, gets built in this scenario because you could sell to the electricity market, say 20% of the time, and to the hydrogen market 80% of the time, and the economics suddenly start to work out. So there's a lot of opportunities for other markets to grow because of the new market pull that comes out of this. Next slide, please. And my final slide with any data on it is from a different analysis. This is from what we call the LA100 Project, where NREL did a lot of work for LADWP to look at their 100% renewable electricity standards and scenarios that it would take to be able to achieve that scenario. You can see the URL here if you want to read a lot about it or a lot about the report and the work that was done there. But one of the key findings I would say here, this shows capacity for generation. And one of the key lessons to learn here is that if we're going to achieve, say, 100% renewables or 100% renewables plus nuclear, we're going to need a lot of dispatchable generation, and hydrogen and fossil energy being burnt to be able to do that are the key opportunities for doing that. So if there are those policy drivers, this is a key need. It's not a huge hydrogen user, but it's a key need in terms of overall balancing and meeting our electricity reliability and resilience requirements. And my final slide just shows a few different, or summarizes a few of my conclusions. Economic potential is 2.2 to 4 times the current annual consumption, even without carbon policies. With carbon policies, as Rob showed, it's 7 times to 11 times, which is in my report, but I didn't show. Increased hydrogen market size can happen with many different sources, including low temperature electrolyzers, and it can increase the total renewable energy generation by quite a bit. So there's a synergy in terms of those markets. And as I mentioned, these can be larger. So with that, I'll close and turn it back over to Peter for the next presentation by Sanal. And appreciate all your time, and feel free to ask questions in the chat and I'll try to respond to them. Thank you.
All right, thanks, Mark. That was very informative. So our next speaker is Sonal Patel, and she's from Power Magazine. She's a well-known author in the energy field, and she writes a column in the energy sector weekly, and many of you have read her articles. She's a multimedia journalist, and she's won 2 national awards for her articles. So Sonal is going to talk to us about the cost of hydrogen power. And Sonal, why don't you begin, just talk a little bit about Power Magazine.
Sure, thank you. We are a publication that primarily covers the power generation industry across the world. So we have a global readership and we cover all sorts of ongoings everywhere. The interesting thing about power is that it's 140 years old, or it will be next year. And we're kind of really proud of that, just because of just the sheer landscape and historical relevance of change in this sector. And this is a decade, and that's like no other, I think, this magazine has shed any light on. So I want to give you a very brief update, overview on what we're seeing from our perspective at the magazine. We tend to look at this as journalists, meaning we take information that is parsed to us. We don't necessarily make any forecasts. we are trying to make sense of the industry as it is now. So, you know, at Power, it feels like every day of the week, we're fielding more news from the industry that we cover, which is worldwide, and, you know, about achievements or plans that concern hydrogen. And as it affects the power sector, we tend to look at it from an end use standpoint. So the potential of hydrogen production to really ramp up the global electricity demand and consumption, but also with the power sector as an end user to use hydrogen as a fuel in power generation applications, such as fuel cells and gas turbines. So there's really interesting ongoings in both respects right now from a technology perspective, really mainly involving efficiency conversion. So as Rob has touched on, hydrogen can be produced. Would you go to the next slide, please? Hydrogen can be produced in various ways, again, from fossil, using power and for water electrolysis, or direct processes using SMR gasification, methane pyrolysis for turquoise hydrogen. On the carbon-free side, without CCUS, that will involve renewable power and nuclear power for green and pink hydrogen. As Mark has pointed out, the biggest impact could be to massively increase the market size and available power from variable generation, but also potentially for nuclear power. So how much power will be actually needed to support a hydrogen economy is a really good question that we always look into. And there are several really remarkable estimates and still a lot of controversy about where priorities should be. So for example, just this week, the International Energy Agency pushed out its first ever comprehensive roadmap to net zero emissions by 2050. The agency has been a really strong proponent of electricity security. And it has come under fire by some of its critics because it gives coal and gas a role in the transition. But in its net zero pathway this week, it turned course and basically suggested no new investment in fossil fuel supply projects will be needed. So it calls instead for an annual additions globally of solar PV to reach 630 gigawatts and 390 gigawatts of wind, which is 4 times the levels set in 2020. So by 2050, the vision is 90% of power generation will come from renewables. But on the other hand, it suggests a massive ramp up of electricity demand. So demand could more than double in its period to 2050. And remarkably, the largest rise is to produce hydrogen and in industry. So the IEA says that merchant hydrogen produced using electrolysis will require around 12,000 terawatt hours in 2050. And so just for some perspective, that's more than the demand in China and the US combined today. So under the net zero scenario, by 2030, which is in 9 years, we're looking at some 50% of low carbon hydrogen coming from electrolysis and the remainder from coal and gas with CCUS and gas blending. But it depends on the region. And as Rob has fleshed out already, we're looking at tremendous new infrastructure needs. We're talking about really rapid innovation progress through R&D, demonstration, and initial deployment. The IEA's net zero scenario, again, an optimistic scenario, envisions 850 gigawatts of electrolyzer capacity by 2030, and 1 terawatts of annual solar and wind additions. And by 2025, we're looking at 3,600 gigawatts of electrolyzer capacity. And that's assuming CCS deployments occur on a wide scale at fossil plants. If not, we're looking at 2,000 gigawatts more. And an additional 9,000 terawatt hours of electricity. So today, just to give you some context, we have only 0.3 gigawatts of electrolyzer capacity, 300 megawatts deployed worldwide. So would you go to the next slide, please? While water electrolyzers are already available on the market, today there are 7 plants in operation that are demonstrating at commercial scale hydrogen production from natural gas. Right now, the choice between the two looks to be an economic one because mainly the cost of natural gas and power, but also whether CCUS is available is another factor. The cost today for producing blue carbon produced with natural gas and CCUS is around $1.5 to $2.9 per kilogram. The cost of producing hydrogen from renewables is about $3 $6.50 to $7.50 per kilogram, but it varies really, really greatly, as we'll see. The goal is to get green hydrogen to $1.50 per kilogram. So very quick, on the slide is a graphic from the International Renewable Energy Agency report. This is a report from December, so quite recent, that delves really deeply into the multiple moving parts that could affect the green hydrogen costs. Basically suggests that the production cost of green hydrogen will depend on the investment cost of the electrolyzers, their capacity factors, which is the measure of how much the electrolyzer will actually be used, and the cost of power produced from renewable energy. So this graphic assumes that an efficiency of 65% at lower heating value and a fixed operation cost of 3% of the capital costs, with a lifetime of the electrolyzer set at about 20 years. So what it's saying essentially is the more load hours, the smaller the contribution from the investment costs of the total per kilogram cost, but the energy price becomes a more relevant cost component. This is a big issue for industry. Can you please move to the next slide? For natural gas with CCUS, production costs hinge on gas costs, typically accounting for 15 to 55% of the production costs. For water electrolysis, the push to lower costs will hinge on learning effects, economies of scale, and this crucial aim to tamp down CapEx costs, as well as lowering costs for low carbon electricity. So according to the Hydrogen Council, which is a notable initiative led by CEOs of more than 100 companies across the entire value chain, this is kind of like the creme of the industry spearheading a hydrogen effort. This crucial aspect of lowering power costs is going to be dependent on renewable sources, but the Council is optimistic that renewable costs in regions with optimal resources like Australia, Chile, North Africa, and Middle East will fall fast because they've already made substantial declines, and in some places they're already competitive with a lot of baseload power. So the Council says a scale up of electrolyzer capacity of about 90 gigawatts by 2030, and that's, you remember, a tiny fraction of what the IEA is calling for, which is 850 gigawatts this week, could boost rapid industrialization of the electrolyzer value chain. It says industry has already announced electrolyzer capacity increases to more than about 3 gigawatts per year. So if that happens, we could see electrolyzer system costs, which include stack and balance of plant, fall really dramatically, but it's also counting on a mass build out of purpose-built renewables, which can boost utilization. So we're looking essentially at a virtual overbuilding of renewable supply versus electrolyzer capacity. Now, this is a really important point in the cost discussion from industry's perspective, because there has to be some realization of the indirect costs associated with the renewables build out and the investment that we'll need. So earlier this year, for example, I talked to a GE executive when GE rolled out its climate commitment. And he basically told me, when you look at the amount of capital we have in models through 2050, even if 10 trillion is deployed in renewables, we're still going to have a gap roughly of a third of the electricity that the world needs, and that's if there's no fossil fuels. So assuming we have the power and we have the scale up, the Hydrogen Council suggests that renewable hydrogen production costs could decline to $1.4 to $2.3 per kilogram by 2030. And again, that varies by region. So it says essentially that renewable and gray hydrogen could hit cost parity in the best regions by 2028, and in average regions by 2032 and 2034. Along with renewable hydrogen production, where the Council is very optimistic about the better CO2 capture rates, low capex requirements for low carbon hydrogen. And it suggests it can be a complementary source, a complementary mode of production to renewable hydrogen. It says that if carbon transportation and storage sites are developed at low scale, then low carbon hydrogen could break even with gray hydrogen by the end of the decade. Next slide, please. So let's hone in now to talk about what a scale-up demands. We've seen demonstrations underway for hydrogen production at commercial scale from natural gas with CCUS. The largest water electrolyzer project that I'm aware of is a 10 megawatt alkaline electrolyzer, and that's at the Fukushima Hydrogen Energy Research Field in Japan. By our last estimation, though, the enthusiasm is really tangible. So today, we're seeing 22 gigawatt scale projects in the pipeline, which is roughly 154 gigawatts. So for the most part, we're talking about multi-million-dollar projects. The 14 gigawatt Asian renewable energy hub in Western Australia, for example, which will use 16 gigawatts of onshore wind, 10 gigawatts of solar power, was going to cost $36 billion. There's a 1 gigawatt project in Portugal called H2 Signs, and it's expected to cost 1.5 billion euros, or about $1.5 billion, $1.8 billion. Pardon me. Developers of the one gigawatt advanced clean energy storage project in Utah just last week said they would seek a $595 million loan guarantee from the Department of Energy, but it's still unclear how much of that total cost that will finance. So for the most part, would you go to the next slide, please? In the power sector, we're looking really closely at how electrolyzer economics are going to pan out. We have challenges right now facing the electrolyzer industry, procurement of materials. We have materials like iridium and platinum, which are scarce at this point. And then we're really looking at the conversion efficiency losses to tackle low load, because that is going to mean something big for flexibility and what those electrolyzers can actually do to function in the value chain. Would you go to the next slide, please? So the good news is we have an extremely great level of commitment. So far, 75 countries representing half the world have net zero ambitions. We have 30 of them have hydrogen specific strategies. There's 70 billion that governments have pledged. There seems to be this very determined ramp up of electrolyzer capacity, which is great. Would you go to the next slide, please? So every day there are new developments, new viewpoints, new projects, technology breakthroughs, new scenarios, economic and business models to make this work. I've outlined here just 3 perspectives. There are hundreds of others, with some companies like Norwegian electrolyzer maker NREL setting a target to get to costs of $1.50 per kilogram by 2025. Collaborations also pushing for cost-focused development. Just on Monday, Green Hydrogen Coalition in conjunction with the Los Angeles Department of Water and Power launched High Deal, which is an initiative that's going to work to achieve at-scale green hydrogen procurement at $1.50 per kilogram in the Los Angeles basin by 2030. So, I would note that the space is, with respect to the electrolyzer efficiency, is developing. And again, from a power generation perspective, to use power to produce hydrogen and hydrogen to produce power is also becoming extremely competitive. And that includes in the the development for hydrogen capable gas turbines. So, I think where the industry is at this point is kind of balancing this idea that we have no sense of what the costs are, but there is real optimism that's really bolstered by value. So value versus cost. The value of hydrogen is rooted in its future role in the way we've been consuming and producing power, and its effect on the march toward decarbonization. And this, by all indications, the power sector is really poised to play a tremendous role in looking ahead. So I think we can queue up Peter.
Thanks very much, Fenel. So I think the big message there is that the costs are coming down. The question is, at what point will there be parity, and how low will the cost of hydrogen go per kilogram? But definitely you can see that the costs are coming down. So we're now going to move over to the transportation sector. And our next speaker is Bob Weiner, who's the Director of the Energy and Environmental Research Group at Toyota North America. Bob, the floor is yours.
Thank you, Peter. Next slide, please. So I'd like to start with sort of an all-encompassing comment, is that, you know, we sell to consumers, and consumers in this country demand choice. So our focus is really to provide a broad portfolio of electric drive. And you can see by this slide, it includes our core competency, which is hybridization. This is something we've been doing 20 years. Over 4 million hybrids have been sold in this country. And this year we expect 25% of our new vehicle sales to be hybrid. Related to that, we have plug-in hybrids. We have taken that hybrid technology and applied it to a fuel cell vehicle that I'll talk a lot more about today. And then we also have battery electric vehicles coming. So I think this just gives you a little bit of a background that, you know, we're not just all about hydrogen, we're all about satisfying the customer and meeting the climate challenges and goals that the country has in front of it. And we just believe in a variety of options. So when we look at the fuel cell Mirai, which is our fuel cell vehicle, we just introduced a new one this year. And hydrogen vehicles in general in California have sold now over 10,000 light-duty fuel cell vehicles. So between Toyota, Honda, and Hyundai, there are now 10,000 of these vehicles on the road being driven every day. Another point that is shown on this slide is that the technology is very scalable. So from the basic light-duty platform, you can, and I'll explain this a little later in the next few slides, is it can be expanded very easily to larger and larger vehicles. So next slide, please. So I mentioned scalability of the technology. So on the left-hand side is a cutaway of a fuel cell vehicle. It's actually our first generation Mirai that came out in 2015. But the point is that you can take those systems, the fuel cell stack, the hydrogen tanks, the control systems, and double them up, for example, and put them into a tractor trailer or a transit bus. And now you have a zero emission vehicle that can haul, you know, either 80,000 pound loads or 30 to 40 passengers in a transit bus, zero emissions, and still refuel quickly as their liquid fueled counterparts. We can also adjust the size of the battery and the storage for medium duty trucks. So this technology is very easy to install in delivery vans, trucks, and that's being done in Japan as well as in Europe. And then finally, there's many other applications for hydrogen fuel cell technology, everything from marine to a lot of applications in industrial services, forklift trucks, equipment for airports and ports, stationary power plants, as well as rail. So all of these are because of this easy scalability of the technology. Next slide, please. So what is Toyota specifically doing in this space? Well, first, and is probably our largest heavy-duty project. It is the Portal project, where we're taking our fuel cell systems out of the same system that's used in our Mirai fuel cell sedan and integrating that into tractor trailers. These tractors will take cargo containers from the ports of Long Beach and Los Angeles and deliver them to different locations within the LA basin. Oftentimes, these are through disadvantaged communities that have serious health problems due to the emissions produced on the roads nearby their communities. So being able to take some older, dirty diesel trucks off the road provides some real-time health benefits to the communities around these ports. So that, in addition to climate benefits of hydrogen fuel cells, is a real plus for the communities. We're also looking at, in Japan, medium-duty vehicles, as well as we've built 100 transit buses. They're 10-meter transit buses for the Tokyo Olympics. Hopefully those will be used here in the next few months. Regardless whether they're used or not, they will go into daily transit service at different locations around Japan after the Olympics. The other truck, the white one in the center bottom, is one by actually one of our group companies, Hyundai. They are in the process of taking our fuel cell system, integrating it into one of their vehicles, and we'll be bringing that demonstration of that vehicle here shortly. And I mentioned some of the other medium-duty forklift trucks and utility tractors that are possible to power by fuel cells. Next slide, please. So we have a very large project at the ports of Long Beach and Los Angeles. The name's a mouthful. It's called the ZANZIF Project, and I won't bore you with the meaning of the acronym there, but basically what it is, it's to bring 10 of these fuel cell Class 8 tractors into daily service with 4 different suppliers or 4 different operators, including UPS, Toyota Logistics, as well as a couple of other smaller logistics companies that operate vehicles out of the port. We are currently testing our prototype trucks, and the 10 production vehicles are complete. They're just going through finalized shakedown testing before they're delivered to the port. These vehicles have the same load carrying capabilities as a standard diesel truck, actually will out-accelerate a diesel truck and can travel 300 miles on a fill of hydrogen. That will allow them to make deliveries throughout the LA basin. In addition to the station, the hydrogen station that we're building at the ports of Long Beach and Los Angeles, we are going to build a station inland that will extend the range of these vehicles even further to cover most of the LA basin. And because they're quickly refuelable, typically a diesel truck this size takes about 10 to 15 minutes to refuel. The hydrogen versions, it's approximately the same amount of time. That means it can operate for extended periods of time, you know, with multiple drivers and not have to sit and be recharged. Next slide, please. So at the port facility, we are also generating renewable hydrogen on site. So this is done by purchasing biomethane from agricultural waste in the Central Valley. That then is used in a fuel cell. It's a high temperature fuel cell on site that generates electricity, heat, and excess hydrogen. So you feed in this biomethane, which is basically renewable natural gas, into the fuel cell, and one of the outputs is hydrogen. That hydrogen then is used to fuel our tractor trailer trucks, as well as all the Mirais that are coming off the ships from Japan. So the Mirai itself is built in Japan, imported with the fuel tanks that are basically empty. Those are refueled at the port before they go out to the dealers for delivery to customers. Next slide, please. So what does this look like? Well, on the upper left, you can see how a tractor trailer would be refueled. We are currently using the system that we use on light duty vehicles, but instead of one nozzle, we use 2 nozzles. The lower left is the H2 storage, where you have the hydrogen stored at high pressure in the tanks, the tube tanks on the left-hand side, and then that hydrogen is dispensed in the vehicle at high pressures. The dispensers are there on the upper right, not too dissimilar from a gasoline dispenser. Again, as I had mentioned, for a light-duty vehicle, that's 3 to 5 minutes to refuel, just like your gasoline vehicle, and then that gives you 300 to 400 mile range, depending on the particular vehicle. And then on the lower right is the overhead view of the heavy-duty refueling. And that's a much larger facility because you could expect queuing from the tractor trailers as they refuel at the end of a shift or at the beginning of a shift. So you need a little bit more space for a heavy-duty refueling facility. Next slide, please. So I'd just like to finish up with the need for feedstock and vehicle diversification to assure success of hydrogen and fuel cells. So on the feedstock side, as was mentioned earlier by a number of speakers, you can get hydrogen a variety of different ways. And I think it's important to remember that all low carbon hydrogen options are viable, and it really depends on what part of the country you're in. So in parts of the country, for example, Texas, that have a lot of natural gas and places to store the captured carbon, that would make sense. But in other places that have a lot of renewables, you can make the hydrogen through electrolysis from renewable electricity. Next, I guess animation. There you go. But we also need diversification of the types of vehicles. So you need passenger vehicles because that light duty scale drives fuel cell volumes and drives down the cost of the fuel cell system. So basically the engine under the hood is the volumes and costs are driven by the light duty application. Next slide. On the commercial side, you need the commercial vehicles for heavy duty scale to increase fuel demand and drive down fuel costs. So that combination, you hit the slide one more time, gives you this ability to grow the demand for hydrogen and the supply of fuel cell technology and move that along quickly. So that's the end of my presentation. I'll pass it back to Pete, and then I guess my colleague from Honda will speak.
Yeah, and just before we leave you, Bob, you spoke about the production project at the Port of Long Beach. Are there other projects like that underway? Are you going to stay in Southern California, or do you plan to go elsewhere in the country?
We are working on a number of different potential projects. Nothing has been made public yet, but this is just the first of what we hope to be a number of port-type projects.
Great, great. Okay, so our next speaker then will be Ryan Hardy, who's an engineer and division head of the CASE and Energy Development Division of Honda, American Honda Motor North Company. And CASE stands for Connected, Autonomous, Shared Electric and Energy. So Ryan, the floor is yours.
Awesome. Thanks, Peter. Thanks to the USEA for including me in this. Next slide, please. I would like to say that I agree and appreciate everything that Bob said about customer choice and the environmental benefit of EVs and fuel cell vehicles. I have three main points in my presentation here. Number one, renewable energy is key to achieving Honda's 2050 carbon neutrality goal. I think most corporations and businesses have long-term carbon reduction roadmaps, and really renewable energy is at the center of ours. Number two, vehicle grid integration and hydrogen energy storage are key to success with renewable energy adoption. And three, electric vehicles and hydrogen fuel cell vehicles can enable some new values of personal mobility. Honda's very optimistic about the future of EVs and fuel cell vehicles, and we think we can express some new characteristics from these vehicles in the market that people will enjoy. So next slide, please. As a corporation, our product strategy is based on our environmental vision, which is the realizing the joy and freedom of mobility and a sustainable society where people can enjoy life. And this really is instructive of all the products and services that our company provides. Next slide. Our goal is to be carbon neutral by 2050 by reducing, eliminating, or offsetting CO2 from our products and operations. And so this really is central to our vision. So next slide. So towards that, we've developed what we call the triple zero goals. One is carbon neutrality for all of our products and facilities. Two is 100% use of sustainable materials. And I think hydrogen as an industry has a huge role to play in generating replacements for fossil fuels, for petrochemicals and plastics and materials that we use in making and manufacturing cars. And I want to highlight that as a need of our company towards a sustainable society. And of course, clean energy, 100% utilization of renewable energy, including solar, wind, and geothermal. Those are the core of our 000 concept. Next slide. And so the themes are expressed by our product lineup, which includes the electrification of our products, automobiles, motorcycles, power equipment, aircraft. We have a central strategy around batteries, including for light mobilities and swappable battery products. We want to expand the use of hydrogen fuel cells across our products and across new product concepts. All of these need to be supplied by what Honda's calling a multi-pathway of energy, which encompasses electricity and hydrogen, and making use of the interplay between electricity and hydrogen through infrastructure-linked smart power projects, such as what Bob showed for the ports of Long Beach. And then all of it is based on products that make use of sustainable materials as well. Next slide. Towards the electrification of products, automobiles make up maybe more than 80% of Honda's overall CO2 and manufacturing impact. And 40% by 2030 of our automobile products globally will be made of electric vehicle and fuel cell vehicles. By 2035, 80% and 100% by 2040. So this is a big change, and it's coming quickly. And it's coming not just to Honda, but to automobile makers globally. And fundamentally, next slide. Fundamentally, all of the energy that is needed to fuel those electric and hydrogen fuel cell products needs to come from zero carbon sources in order to actually achieve the CO2 reduction goals that we have for our products and society has for our products in general. So without the means of directing zero carbon energy to these, we simply can't achieve those society's long-term CO2 reduction goals. So next slide. So towards the vision for our own operations, we've already contracted for more than 60% of the electricity that we use in North America from renewable wind and solar projects by 2024 towards the 100% goal. Now, through this experience, we're understanding and learning how to expand renewable energy usage and supply to our products as well as our operations. And take the next slide. So this is a bit of a complex slide, but the concept is simple. Transportation energy demand has the ability to completely decouple the energy supply from renewable energy from the energy demand by the transportation vehicles themselves. So electric vehicles and managing the charge timing of electric vehicles can make use of charging when renewable energy is generating and stopping charging when it is not. And we can meet the moment-to-moment balancing needs of the electric grid through managing the charging, including discharging using vehicle-to-grid technologies of vehicle batteries in order to match the daily and moment-to-moment energy supply and demand of a renewable electric grid. To manage seasonal differences in how renewable electricity is generated, hydrogen has, I think, a huge role to play in terms of decoupling the energy generation and supply into a renewable energy-based hydrogen system from the demand of transportation. And transportation can form a good, solid demand set for that renewable hydrogen, which provides a value stream for the hydrogen. So one of the challenges of renewable energy and the way that our electricity markets currently operate is that when there's too much electricity, the wholesale market prices for electricity go negative. And that's a big disincentive to the next investor who wants to build a wind farm or a solar field. We need a giant source of dispatchable, flexible demand that hydrogen can bring to the renewable energy industry in order to soak up the surplus not only on an hourly basis, but on a seasonal basis, in order to provide the incentive to invest in the next solar plant, in the next wind plant. And so that's really important, that hydrogen can be that source of flexible, dispatchable load on a weekly and seasonal basis, and electricity through managing charging of EVs can provide that on a daily basis. So those are important concepts. So we call this vehicle grid integration, and it's key to our all of society's ability to meet a renewable energy future. Next slide. we've developed a program we call Honda Smart Charge, which does this for vehicle charging. And we think that this will become an important part of the electric vehicle experience, where through tools like Honda Smart Charge, electric utilities and electric grid operators can recruit electric vehicle drivers such that their cars are charged when it's good for society, good for the grid, good for renewable energy generation, and stop charging when local distribution grids are congested, when wholesale generation relies on fossil fuels. And so we've seen on a daily basis and hour per hour, we can meet the vehicle driving demand of customers, meet their need for full batteries when they need them, while also mitigating the renewable energy integration issues and reducing CO2 emissions from fossil fuels. So this will become a core part of the experience of driving an EV. And fundamentally, people buy electric cars and buy cars because they want to get somewhere. So having the customer and having the vehicle as part of that communication network is critically important to the satisfaction of the product to the customer in the future. Next slide. Some of the other aspects of electric vehicles that are, I think, very appealing to consumers in the future is because of the stored energy on board of electric and hydrogen fuel cell vehicles, we can provide home backup power for resiliency. And so at Honda Smart Home at UC Davis, we have demonstrated this vision with since 2014, providing a home backup power. I was impressed yesterday, Ford with the F-150 rollout showed off the same vision. Next slide. And not just for home scale, we can provide community electricity and energy resilience by, especially with fuel cell vehicles, moving giant supplies of energy storage to the places where they're needed to provide community resilience to people. So either it's personal level energy electricity usage, such as with Power Exporter, or bulk community level to back up a substation from a hydrogen bus. Those concepts are possible with electric and fuel cell vehicles. Next slide. And so fundamentally, though, the challenge of marketing and selling and getting the benefits from these vehicles is we have to sell them. We have to get them into the market. In order to achieve the renewable energy portion, we need kind of transportation to be a key part of any energy storage policy that needs to support the sale and marketing of EVs to get them into customers' hands. The vehicle integration benefits, again, we know that we need to work with utilities. We need to do things in such a way that electric vehicle customers benefit, that it drives demand. We're able to get these vehicles into the market. And same thing with the new values of personal mobility from EVs and fuel cell vehicles. Fundamentally, people need to get where they're going. One of the biggest barriers is public refueling infrastructure. When people are considering electric vehicles or fuel cell vehicles, they need to know how and where they're going to recharge them and where they can go. And so fundamentally, in order to achieve the benefits and for people to realize these new values, we need support for public refueling infrastructure for EVs and fuel cell vehicles. And with that, I'll turn it back to Peter, and thank you very much.
Well, thanks very much, Ryan. And just before we leave your presentation, you had images of the Clarity Electric and Clarity Fuel Cell. Are they comparably priced?
Both are. Well, the fuel cell is a more premium product. It's definitely higher priced in the market.
Okay.
Mind the prices, but it is a little bit higher.
Okay. All right. Well, it's good to know. Okay. So then let's just go ahead and speak about some of the tax incentives and where we're going here. And just to let's go to the next slide for a moment here. If you think about renewables tax incentives, it's a bit of a hodgepodge. We've got the investment tax credit for solar projects and fuel cells. We've got either the investment tax credit or the production credit for wind and geothermal and biomass. And then we've got the production tax credit only for carbon capture and sequestration. And that actually is something that it came up in one of the questions and is relevant for blue hydrogen. So that is, if you're capturing the carbon from a gas plant and securing it on the ground, that would be eligible for potentially a $50 a ton credit. So that's good news, and that will continue. In fact, it might even be more generous going forward. Let's go to the next slide. And when you look at just the very specific incentives for hydrogen, there really aren't very many. There are some limited incentives for the hydrogen fuel vehicles, $8,000 to $40,000, depending on the weight of the vehicle. There's a $30,000 credit for the refueling or the recharging station. And then there is a 26% credit for hydrogen fuel cells. So let's go to the next slide. But I think the outlook is actually pretty optimistic. There's just been a ton of legislation proposed. And the most recent one is the Clean Energy Act for America that was proposed by Senator Wyden in April. And that would have lots of incentives for clean electricity. The investors would have the choice of either a reduction credit of 2.5 cents per kilowatt hour or an investment tax credit of up to 30%. And this would also have a very important clean energy fuel credit of $1 a gallon, which depending on, or a gallon equivalent, depending on how you do the math, that might be $1 per kilogram or maybe 50 cents per kilogram. But it, but if you see the price of hydrogen dropping, to let's say $3 a kilogram pretty soon, $1 or 50% cents per kilogram is pretty much of a nice incentive. And then you're going to see an increase in the credit for the charging stations, currently $30,000 to going up to $200,000. So, if you just take a look at the Wyden legislation, I think that and that is probably the key legislation to look at this stage. There is actually a lot of incentive or a lot of movement toward increasing the incentives for hydrogen. And that's just one piece of legislation. There are just, every other week there is another bill. There was one in December by Senators Young and Whitehouse called the very specific to hydrogen, which would add hydrogen to the production credit, which would also be covered by the Wyden legislation. And the Green Act would expand the ITC credit to include energy storage, which would include hydrogen storage. So let's go to the next slide. And then just looking at, where does President Biden stand on this? Well, it's really hard to tell. We will know for sure by next week, because next week is when the Green Book is released. And the Green Book really details the proposed legislation that the administration has. So that'll be May 27th. But we can look at the American Jobs Plan proposals, and we see one that's very specific that talks about the development of hydrogen demonstration plants in distressed communities. And it adds very specifically a new hydrogen tax credit. So it's certainly on the radar screen in terms of the president's proposals, and I would say for sure that we're going to see some activity in this area. We just don't know what it is. If I had to predict, it would be probably closer to what's in the Clean America Act that Senator Wyden has proposed. So that brings us to a conclusion of the program. We have a couple of questions that I'd like to see if we can get some reaction on from some of the panelists. And the first one that came up is probably for Mark. It has to do with the impact on the development of the hydrogen industry on the nuclear industry.
So as most of you probably know, the nuclear industry in the US, it has been very challenged today as the price of electricity has been dropping across the US due to low cost natural gas and the proliferation of wind and solar PV. And there's been a number of nuclear plants that have been shut down. Our analysis showed, and some of those mustard orange bars I showed in some of my slides showed the potential benefit of producing hydrogen instead of nuclear technologies. A lot of that hydrogen was produced by nuclear power plants that would be able to produce it at the equivalent of $25 per megawatt electricity. So hydrogen has the opportunity to be able to both keep those nuclear power plants operating and to be produced at a low competitive price for green hydrogen from those locations. Therefore, we've done some analysis with Xcel Energy on 2 of their nuclear power plants in Minnesota. It's ongoing right now, but we're finding opportunities for those plants to be able to provide essentially peaking electricity or capacity payment type values to the grid as a whole to be able to produce electricity at these kind of peaking needed, produce hydrogen most of the time, and be able to compete because it is green or pink, as some people put it, in terms of the hydrogen color.
Thank you. So another question that came up was about.
Can I just jump in there real quick and add on to that?
Yes, go ahead.
From our perspective, one of the most interesting cases for producing hydrogen is where you have renewable energy curtailment. So you have so much renewables on the grid that they don't have anywhere to use that power, and prices sometimes go negative. I think if you're able to pair hydrogen electrolyzer plants in places like Texas, where you often have curtailment, that is one of the most attractive ways to produce hydrogen, and one of the most cost effective, because once you have that capital expenditure complete, the source of your electricity and the cost of your electricity is one of the most important components there. So curtailment pairing with hydrogen production is a pretty attractive opportunity too.
Great. So we had another question about recharging stations, and I mentioned that there's a credit of $30,000 right now for a recharging station, and that it will go up to $200,000. Could somebody address what one would expect the cost of a hydrogen recharging station is?
Yeah, I can chat a little bit about that. The hydrogen station is really, it's more expensive than an electric vehicle charger, of course. The key point we have to remember is throughput. So the amount of vehicles you can refuel in a given amount of time. So yes, a hydrogen station might be $1 million or more, but that's going to be able to fuel 2 to 4 vehicles pretty much continuously all day long. So you're not going to be able to get that sort of throughput through a equivalent battery charger. So yes, the cost is greater, but the capacity of a station is much greater, and it can service in the neighborhood, hundreds if not thousands of cars over the course of a given, let's say, month, where a single or even multiple chargers can't keep that many vehicles recharged. So we like to think of it as the amount of vehicles served by an individual investment.
Ryan, did you want to add on to that?
Yeah, I could just add, I think Bob hit it right, where the infrastructure dollars spent per vehicle refueled for public refueling infrastructure for electricity and hydrogen ends up being close to the same number on a dollars per vehicle served. And so that's kind of an important consideration long term.
Great.
Mentally, both.
So we had another question, and that was, again, is to Bob and Ryan. And could you project the size of the hydrogen light vehicle market by 2030? at least in the US?
That's a tough one because it's you know, one, those are you know, often very proprietary numbers. I know that we've announced that we can produce up to 30,000 fuel cell systems a year. So, you know, that's a current number. If that were to increase, if there were multiple companies that were able to produce that many fuel cell systems, you could easily see 100,000 vehicles on the road by 2030. Right now, we have 10,000 vehicles. That was the first vehicle, I believe, was the Honda fuel cell vehicle that was introduced in late 2014. Since then, there's roughly 10,000 in California. So 100,000 by the end of the decade seems very, very feasible.
Ryan, you get the last word.
I think I concur with what Bob said. I mean, fundamentally, it's infrastructure limited. We can only deploy vehicles in communities where hydrogen stations exist. And, you know, so far, we're kind of geographically limited in where we can deploy vehicles. Those two things have to grow together. It's an issue of chickens and chicken feed. If you put out chicken feed, you'll find chickens in the neighborhood.
Excellent. Good answer. Mike?
We're done. 1:30.
Great.
So guys, great work. Fantastic content. A lot to digest. It's come a long ways. I've been tracking it, not involved in it, since the days of Governor Schwarzenegger having his hydrogen-powered Hummer go out to rove around town a little bit. And I believe he actually he got bumped by one of Elon Musk's 2 existing prototypes at the time. And that was my first introduction to the battery world and to the hydrogen world. Anyway, thank you all, everybody, very much for the time spent. Very informative. This material will be available on the website, along with the tape recording, video recording of the program here. And Peter and Robert, you guys did an awesome job putting it all together to make this happen. So again, thanks everybody very much, and have a great week.
Thank you very much.
Thank you.
Great. Thank you, everyone.
Thank you.